Thanks, Vikram, and thanks to Huawei for sponsoring the event today. So today, we are sort of going to cover the architecture of ONOS, which is the distributed network operating system. So when we were sort of preparing for this talk, we were sort of trying to figure out how to best cover this. We had the option of sort of going for breadth and sort of or picking a couple of areas and then sort of going into more detail on how those things are architected. We sort of picked the latter option. We felt that would sort of give us a opportunity to sort of choose a couple of areas that are of interest. People have asked about those, and then see how we arrived at the final sort of design decisions and sort of what motivated us, right? So Brian is my colleague here, so he will be also covering part of the presentation. So with that, let's get started. So here's an outline for the talk today. So what we are going to do is basically take a simple example and use it as a motivation for sort of see how that guided us in building ONOS and how it helped us come up with the architecture decisions. And then that sort of is a segue to showing a picture of the block diagram of the ONOS architecture and the different tiers. Then one of the areas that we picked for going into greater detail is basically the distributed store. This is the part that does the distributed state management, and it is at the center of providing high availability and the scale out functionality. Then Brian will take over. He will cover the different service APIs that ONOS offers and sort of provide a template for building new services. And then Brian will also cover, basically do a deep dive into the intent framework. There is a lot of interest about this. This is sort of like the nice northbound abstraction for getting things done from the network. So we are going to cover that, and then we will do a live demo. Basically like a setup of ONOS running on a clustered environment. We'll be able to see it in action at that point. And finally, we will do QA. So in the interest of time and in the interest of getting through the presentation, we would appreciate if you guys hold the questions to the end, and we can cover them at that point. So So the problem we would like to use as a motivating example is how do you set up a flow in a network, right? And what is that you need in order to solve this problem? It's a very simple problem, but the idea is that it will help us tease out some of the features and the requirements that we should have for any good controller. So the first thing you need to do is you need to understand exactly what the network is, right? And that means that you need to be able to in some sense discover the topology that you are dealing with. So SDN provides this nice abstraction of a global network view. It lets you, with that global view, you can do things in a much more optimal fashion than what you can accomplish with distributed protocols, which are sort of legacy sort of things. And once you have this nice global network view, the things that you want to do is you basically compute a set of paths that will let you establish this connectivity between these two end hosts. Once you do that, and once you know what constraints you have, you basically make a selection, right? You select one or more paths. For example, you could select more paths for if you need a backup to be programmed into the data plane. And once you do that, you sort of compute the flow mods that you need to apply, right? And once you have the flow mods, you need to be able to program the data plane so that these things are on the data plane. And next what you have is a process of installing these flow mods on the data plane, right? And you need to be able to do this in a manner that doesn't drop packets while you're doing it. Now, our goal is to not just establish connectivity. Our goal is to also maintain that connectivity even in the face of data plane failures, right? An important feature that any good controller should provide is an ability to monitor the state of the network and be able to react to events that are happening in the data plane. So in our case, what that means is that you identify the flows that are impacted by a switch failure or a link failure and essentially fix those flows. So this basically lets us come up with a list of features that we should expect from a good network controller, right? So you have your global network view, you have the ability to compute paths, you have the ability to compute flow mods and the ability to install them, and also the ability to monitor and react to events that are happening in the network. Now, in any realistic scenario, you need to be able to do this with high availability and at scale. Right? You need to be able to deal with failures happening in the data plane as well as the control plane. And also, in a real production scenario, you cannot like radically change your architecture once the size of your network grows. So whatever solution you come up with should still be valid even if the size of the network grows tenfold, for example. So that basically is one of the things that you design. Now, again, in any realistic network, you are not just dealing with like a homogeneous set of switches. You will have a bunch of switches, bunch of devices, that speak different protocols, have different capabilities, and any good controller should be able to interface with all these devices and still be able to do the flow programming in this particular case. Now, what that calls for is a southbound that is extensible and it is pluggable. Now, what we looked so far is actually a very simple example, right? Now, in any realistic deployment, you probably have like these middle boxes or services, which can impact how you compute paths in a complicated way, right? So while a simple graph algorithm based on Dijkstra's might be okay for like a simple flow, but once you bring in like services like this, and you need to be able to sort of ensure your flows, go through these services, you end up with a complicated, path computation algorithm. What we expect is that any good controller is built in a modular fashion so that you can customize parts of it that you need to change and extend, while retaining the capability to reuse stuff that is already there and for which a generic functionality is okay. So with this, we can sort of like look at this architecture diagram of ONOS that sort of, explains how the different tiers are laid out and what responsibilities lie at each tier, right? So you have the southbound, which is responsible for monitoring the network and also, sort of has the ability to program the network. So this is the layer where, you have protocol-specific adapters that lets you, interface with different kinds of devices running different types of protocols. At the top, you have this, nice northbound abstraction that lets applications get the desired result by programming the network. So basically, this offers a higher level language that you want to speak to the controller, so that the controller can do the desired end result or produce the desired end result. And in the middle of all this, we have this distributed core, which is responsible for state management. And that is the part that I'm going to cover in more detail in the next set of slides. So, as I said, the distributed core is the part that is responsible for doing state management and also providing features that are at the end give you high availability and the scale out functionality, right? So one key thing in ONOS is that we sort of use different techniques for dealing with state that have different properties. As I will go into more detail in the subsequent set of slides, an example here is if you're dealing with the global network view. It's a piece of state that is heavily used. Almost every application uses that as a starting point for whatever it is doing. How you manage that state might be significantly different from how you manage, say, something like flows, right? Where the places where they get read and written are like fairly localized. So we sort of use this distinction in how states are handled and processed to basically use different techniques for managing them. And this is something that I will go into more detail next. So as I said, global network view and how we scale for strong consistency are two things that I will cover in more detail. So let's consider a sort of a distributed control plane and see how one could architect that, right? So you have your network and you have your set of controllers that are working in cohesion to produce basically implement the control plane. So you can have your switches connect to one or more controllers. Usually, like they have more connections for availability reasons, so that even if a single controller is down, you could fall back to a backup controller and still have the ability to program that particular switch. So usually the control plane ensures that one of the switches, one of the controllers that the switch connected to is elected as a master, and this decision is essentially strongly coordinated between the controllers in the control plane. So the guarantee that the controller provides is that at any given point of time, one instance is responsible for communicating with the device, and that in essence serves as the master for that particular switch. So in steady state, you have this situation where each switch basically has a primary connection to one of the controllers and has the ability to fall back to a backup if something goes wrong with the controller. So that basically gives you a situation like this, where if one of the controller has any issues, all the backup connections are activated, and you still have the ability to monitor the state of the network, and also program those switches. So a situation that we have in this particular setup, which you don't have if you're running a single controller, is any given instance only has visibility over a small portion of the network, right? So as you can see, one of these controllers only has direct visibility over 3 switches, and similarly the other controller looks at a couple of switches and so on, right? Now, how do you ensure that given this sort of narrow view of the network, how can you still provide this nice abstraction of a global network view and do so in a manner that is A, well performing, and B, correct, right? So there are a couple of ways in which you can do that, right? Let's say you have a controller and it wants to get a view of the entire network. It has direct visibility over a portion. For the portion of the network that it doesn't know about, it basically asks other controllers to basically ask them to share their view of the network, right? So, and then it can sort of piece together all these different slices and then produce a global network view. The good thing about this is that it actually produces a representation which is correct. I mean, at any given point of time, the view of the network that a given controller has is as close to what it is on the network as possible. Now, the problem with this is that it is actually quite slow. Having to download a portion of the network every single time you want to get a picture of the whole network is going to be slow. So the way most of a traditional way in which this is handled is basically introducing a cache, right? So what you do is instead of going to other controllers every single time, you cache their view of the network, and as long as you basically have that view in the cache, you access it from the cache. But a problem that this solution introduces is that the view that is served from the cache could be different from what is on the network. So how do you ensure that your view is closely tracking the view of the network? So actually, let's look at how this problem is handled in some real systems, right? And also this is an approach that we took in the initial version of ONOS. So there are some lessons to be learned, and hopefully we learned these lessons, and that sort of helped us guide towards our final solution. So typically the way it is done is you have this distributed database. In this particular case, it's a topology store. Again, this database is usually sharded across all the controller instances. So as topology events arrive from the network, each controller essentially stores that topology event in the distributed data store. And whenever a given instance needs to look at the entire picture, it goes to the data store and basically gets all the different events that were previously stored. So what this does is, as events are arriving, you are basically putting them into the data store, and when you want to piece together the entire picture, you load all of that from the data store. This approach is actually not very different from what I described earlier, where when you need to build up this view, you go ask every other controller. In this particular case, you are not directly asking your controller, but you are asking this data store, which is basically partitioned across all the controllers. An experience that we had with this particular solution is that having to download this large view from the distributed data store every single time is slow. And the first thing anyone does when something is slow is basically add a cache, right? And then we have the same problem that I described earlier. How can you ensure that the view served from your cache is in sync with the view in the data store? But more importantly, how do you ensure that it is in sync with the state of the network? Because that is the main goal here. We want whatever view that we have to be closely tracking the state of the network. So that's how do you ensure that the view from your cache is in sync with the network. So let's look at perhaps a simple solution for this problem and see what problems it introduces. So let's view the topology as a state machine, right? And see how we could build a solution based on that. So the way this works, or the way the state machine evolves, is that you have the current state of the topology, and as events arrive, you apply those events to the current state, and then you basically move the state machine to the next state, right? So as events are arriving, you apply them to the current topology, you produce the next version, and then whenever you want to access the current view of the network, you access the state of the state machine. Now the events are things like switch, port, or link up-down events. So as you build up your topology state by applying these events, the idea is that you have in some sense a graph representation of your topology that reflects the state of the network elements. Now let's see how this will work in a scenario like this, right? So we know that a given switch always has a controller that is talking to, right? As I described earlier, this controller is the master for that particular switch. So whenever the switch sends up a network event, that event arrives at the master controller, and what the master controller does is replicate that event to all the other instances, and each instance is maintaining an in-memory topology graph, or in this particular case a state machine, that it applies the event to. So what you have is a fully replicated copy of the topology that is evolved by applying these events that are observed on the network. Now let's look at a small failure scenario, right? So let's say the current master for that switch goes down. We know that the switch falls back to the backup controller and then starts reporting events to that controller. Now when you do that, and that controller replicates those events to all the other instances, you have the following scenario. Let's say that two events arrive at one of the controllers at roughly the same time. And in this particular state machine, the order in which you apply the events to the topology graph is important. The order of applying a port up followed by a port down is not the same as applying them in the reverse order. You will end up with a drastically different end result if you change the order in which these things are applied. And also on the left hand side, you have a scenario where this controller actually missed some of the events, right? It was up to date till the point where the failover happened, but given that it is temporarily down, it actually missed some of the events. So you have the scenario where you have a reordering problem on one end and you have a missed events problem on the other end. Given that these problems can exist, how can you build a solution that sort of addresses these and still gives us the right solution, right? I mean, remember the important end goal here is that we are trying to build a network view that is highly performant, meaning there are lots of reads that are going to this network view. We want to be able to serve those events very quickly, and in this particular solution, the network view is essentially an in-memory representation. So the performance aspect of it is okay, but the correctness aspect of it is very important, right? How can you ensure that the graph that you have is closely tracking the network, right? So remember, that's the main idea here. So let's look at how we can fix this reordering problem, and hopefully that will give us a solution that is both correct and performant. So let me introduce a concept here, right? So we know that at any given point of time, a switch talks to a given controller, which is its master, right? So we have this notion of a mastership term that is closely tracking which controller is the master for a given switch at any given point in time. Whenever the transition happens, we bump up the term number. So the idea is that as a switch changes mastership, you are incrementing the term number, which basically tells us, which, you can think of it as a monotonically increasing sequence number that tracks how many times a switch changed mastership, right? The idea is that in any given term, the switch is sending up events to its controller, which now get numbered. And the way we number those events is by using a combination of the term number and a sequence number. Okay, so while the term number is this, globally consistent, data that we are storing in a consistent data store, the sequence number is actually, it only is locally useful. So a given master is tracking this number on a per switch basis, during its term. So whenever an event arrives at a controller, using purely local information, with very little cost, it labels those events using this scheme. So what you have is this approach for annotating the events, and the idea is that this way of timestamping these events gives us a mechanism to arrive at a complete ordering of all the topology events, right? Well, complete ordering or total ordering of all the topology events from a given switch, but if you extend it to the entire topology, it lets you arrive at a partial ordering of all the topology events. So let's sort of walk through the same example again, but now with these timestamps in place, right? So so switch is switch S1 is in term 1. So basically the controller on the left is managing that particular switch. So whenever event arrives at the controller, it is going to timestamp it using this scheme. So you have term 1 and the event number is 2. So imagine this is the second event in that particular term. And the first thing that the controller does is replicate this event throughout the cluster while preserving the timestamp. Now when the controller fails over, we know that the term number gets incremented, because we know that the mastership election will ensure that we get a higher term number when this happens. And any new event that is sent up to the new controller also gets replicated along with the timestamp. So if you look at how this helps us sort of fix the reordering problem, it's actually pretty straightforward. The controller on the right sees two events, right? Again, these are for the same switch. As you can see, it's for S1, and it basically looks at the two events, looks at the timestamps, and figures out which one to discard, right? So it only takes those events which are more recent and then applies to the topology graph. So if it gets an event which is out of date or stale, it just drops it on the floor.
Does it include timestamp?
No.
If it is in a if all three are synced?
No. So we don't use physical wall clock timestamps. These are logical timestamps. Right. So we don't. A trivial solution is assume a globally sort of in sync clock and then use that to replicate events, but that will break down when clocks are out of sync.
You can call it an event stamp.
Sorry?
You can call it an event stamp.
Yeah.
Yeah.
Yeah, exactly. So I think timestamp is a little misleading, but the idea is that this is a logical timestamp or a logical event stamp.
Question.
Yes.
So what is the second event that actually processed first? So will be
correct. So say for example, if the second event is a port up event, right, and the first event is a port down event, right?
So in this case, it will be the same event.
Yeah. So basically, if you take the second event and process it first, right? The end result is that your graph is still consistent, right? So if the event says that the port is up, you will take that event and then record it. And if you get an old event saying that the port is down, you would just discard it, because you have already processed a more recent event for that particular network element.
What if the controller one comes up again,
Correct.
Again, you get another down event.
So, as I said, when controller 1 comes up, right, it still doesn't have the mastership for that switch. The switch is still talking to the second controller, which is now the master, right? So there are a couple of edge cases that we still haven't considered. So we will get to that, and hopefully that will sort of make this a complete solution. So what you have now in the current setup is you have the ability to deal with reordered messages, right? So you have the ability to detect when an event is stale and then drop it, right? But there is still a possibility of messages getting lost. So remember, like the controller on the left actually lost messages, right? And his topology graph is actually out of date. How do you fix that, right? So, but to summarize till where to the point where I covered, right? So you have this, in this solution, each instance has a entire copy of the network topology in memory, right? Events when they arrive get timestamped using a very low cost method, using purely local information, and then they get broadcasted. And the broadcast mechanism is best effort. So we don't really try to ensure that the messages get in a guaranteed manner. That has problems. That is what I will get next. And whenever on the receiver end you detect a stale event, you basically drop it, right? So the thing that we did not cover is how do you deal with drop messages, right? So you have a situation where some nodes are more up to, or some controller instances are more up to date than others, and you still need to be able to deal with that, right? Because you can have applications running on these instances, and they are essentially looking at the local network view and then making decisions based on that. So you still need a way to identify these differences that are that you see across instances, and then fix them, right? So we basically have a mechanism for doing antientropy, right? So entropy is this sort of like state of disorder in the system, and if you just don't do anything, the disorder keeps growing, right? So if you do work, you can actually reduce the amount of entropy in the system, and that is what we do here. So what we have is a very lightweight sort of gossip style protocol where two nodes get together and then they exchange their views. They do so in an efficient manner. So what they do is they only exchange limited amount of metadata that will let them identify the differences and then fix them, right? So you can imagine that like one guy can basically send his entire network topology view, and the other guy looking at the timestamps figure out like what to take and what to discard. But what we do is we do it in a couple of rounds. So in step 1, one of the guys picks a random node and sends the set of network element IDs and the associated timestamps that he has. And then on the receiver end, you look at the associated timestamps and see if you have events that are more recent, in which case you send those events to the other guy, or you also see if you have events which are old, in which case you ask the other guy to send those events, right? So basically using this lightweight protocol with limited network overhead, you can identify these discrepancies in the network views and then fix them.
Are you meaning timestamp is event stamp or timestamp?
When I say timestamp, it's always logical timestamp, right? Yeah. And another benefit that this approach has is that if you have a new instance that is joining, who has absolutely no sort of idea of what the network looks like, he might just be talking to a set of switches, but he still needs an ability to sort of know about the entire network. So the first gossip or the first anti-entropy interaction he has with another node, which is presumably more up to date, he basically updates his view of the network. So without any special bootstrap mechanism, this gives us an ability to bring newly joining nodes up to date and in sync with everyone else in the system.
How do you number the switches? I mean, how do you number the switches? How do you know that S1 is S1?
So each switch has a unique ID that we, that we assume, right? It's that we just assume. I mean, like there are unique IDs or like
like the same like in bridges they use like serial number or something.
Yeah, it's like a serial number. You can think of that as a unique number. The only thing is this sort of like remains the same across like switch restarts. If that number changes, then obviously you don't know what you're tracking, right? So I have a question there. Okay. So that sort of like summarizes the approach, right? So again, to sort of recap where we started and why this solution is useful, right? So global network view is a very important abstraction that SDN provides, right? It basically says that by having this like global view of the network, you can make decisions which are in some sense more optimal than what you could accomplish with a decentralized protocol, right? But the challenge is, how do you ensure that that view remains accurate as the size of the network grows, as well as in the face of failures in the system, right? And as I described, we have there are various approaches that people do, right? I mean, you could essentially take these events, put in a database, and then go load them every single time. But there are drawbacks to that, and this is a protocol which addresses those.
There are a lot of commercially or open source database available which implement gossip, swim, like Cassandra. You didn't plan to use them?
So, in fact, the first solution that we used is actually based on Cassandra.
And then didn't work?
It actually very slow. So the way we are using it is, again, so for example, what we want here is we want very quick access to the entire topology state, right? And you cannot get more faster than an in-memory copy of the topology locally. And with Cassandra, what we got was essentially the topology graph is distributed across all the instances. So if you want to basically get that view, you have algorithms which will operate on a graph, right? Now, in order to first employ that algorithm, you need to basically piece together that graph. And the way you do it is essentially traverse to the entire topology table in this particular case, and then load the data for each network element.
Well, that's quite understandable. Cassandra is not meant for read, it's meant for write. I write with a comment for that. In most of the cases.
Can you speak up, please? We can't hear the question.
So,
You can repeat the
I'm done
question.
actually, I don't know.
So you can finish the question and I will
My question was just with the choice of implementing the distributed protocol on their own rather than picking up any open source products like Cassandra and using that capabilities. So he explained that it was not coming out at the optimal speed when it comes to reads.
So as I mentioned earlier, right? I mean, there are updates that are to be made to the network view, but it is also fairly read heavy in terms of how often it is accessed, and it is not like we only access a small subset of the topology, but usually the pattern is that you access the entire topology. And when we tried Cassandra, it was not as performant as what we expected.
I mean, does it actually find some correlation with how bit torrents were implemented in distributed system? Then you actually pick up that only view when it's kind of called in, and then you get a copy of that. And you were saying that every controller has a whole view. Instead of that, you actually pick up only that part of view, which you actually does read on rather than picking everything.
So if you have,
how do you scale that thing up? I mean, value.
So
you asked my question.
So is your question?
Example is BitTorrent. How BitTorrent works?
Right. So if I understand how BitTorrent works, I mean each node is basically serving as a seed for certain chunks of a big file.
Yeah.
Right. Yeah. And they advertise it, right? And and then you have a capacity to download, and that capacity is usually dependent on how much you have served up for other clients. So there are some parallels, but I'm not sure if this is.
No, my question is that just to give a bad, I mean, BitTorrent may not be exact similar correlation, but the idea is that you're going to actually bloat out your topology to a very large extent at one time.
Okay.
So does it make sense to actually load everything at one instance, or rather actually load it only when it's needed? That's what BitTorrent does. It kind of replicates to multiple locations when it's something fetched up to figure out, okay, that only those blocks have multiple copies which are accessed more.
I think it's a valid, so how big will the topology be until this approach works, right? At what point does it break down, right? It's a valid point. I think I'll get to it. The idea is that we don't expect that one control cluster will essentially manage a network like that spans the entire United States, for example, right? The idea is that you have clusters which are managing local networks, which are, which can still fit into a single node's memory.
So if it's a local network, why are we bothered about actually talking about things like gossip and all, because there's work on distributed, which are actually working on unreliable things like internet or wireless protocols.
I don't know if you,
I mean, a closed data center, like you have a rack-based systems,
correct.
or 2 racks. I mean, how much packet loss do you? Okay, we are all working on asynchronous networks. We fine, ODUDP and etc.
Yep.
So what is the packet loss there actually? I mean, we talk about gossip and distributed systems when we actually go over internet.
I mean,
Then it means unreliable protocol.
So this is an area where it can also be applied. I know where gossip is applied. I mean, we have used it in other systems as well. Even though the amount of packet loss is negligible in a sort of a rack kind of a setup, but you still need to be able to deal with this particular problem, right? So I mean, you need to be able to detect that.
So I had a question. One set was what he talked about actually, and the other one is you haven't actually solved the problem of inconsistency, because if you have an update happening over a period of time, this is a classic routing problem actually, that while the updates happen, the things can change. So you may be in a state where you will never converge actually, and you will never have a topology consistent.
That's fine. I mean, if you have a network which is always changing, then you have other problems, right? So ultimately, you need to make a decision, right? I mean, you make a decision based on a current view. If by the time you apply the decisions made based on that view to the network changes, you have to deal with anyway, right? That's not a problem that we are trying to solve.
I know those are usually restricted to smaller pockets. With this, basically, you put the churn in a much bigger place. That's really what would happen. So one big database churn happens, whereas a lot of the times the churns are actually very local, and it does not have to be a global event, which it will happen here. That's one comment, and the other one.
We'll probably table this. I mean, I think we can.
The other question also I have is, the events you have are actually very simplistic, the up and down. If any event actually has a side effect, then actually this will not work at all. So in a serious network, you only think Ethernet.
I think we'll get to that, just to sort of go through this. And then...
The other thing which probably has a bug in the system is that one is the leader selection. You pick up one leaders in that 3 node clusters which you have built up. It is mathematically proven that the leader selection actually in the Paxos doesn't work when it's on a distributed network over internet. So this system, I don't know if it can actually map itself to a unreliable distributed system.
Yeah. So that was not the target installation. I mean, this is not meant to run in a sort of a WAN network. I mean, the controller instances are still... Sorry?
And you don't need one.
Sure. We'll get to that. Yeah. So, the general statement that I would like to make at this point is there are solutions which are proposed here that sort of say that whenever you see an event, basically store it in a strongly consistent database. That is how you sort of build up your network state, and whenever you want to read it, basically go to the data store and read it. The idea is that if you have a system where you are essentially observing the state of an external system that you don't control, then we feel that eventual consistency is the best option. Because the idea is to, so if you have a set of replicas, the goal is to not, sort of spend the effort to make sure they are consistent with each other, but to make sure that, your view of the network closely tracks the state of the network, right? Because there are solutions which are proposed which say that, you want to store these events in a sort of a strongly consistent database, perhaps using like a Paxos protocol. But what does it mean if, in a system like this, where you have a network update to accept, but the protocol rejects that update because it cannot maintain replica consistency, right? What we want is an ability to sort of accept that update, but have the mechanism to ensure like the replicas get in sync when when the system settles down. So the other thing that we have in ONOS that sort of like packages all of this together and provides a nice building block for applications to consume is we have this notion of an eventually consistent map, which provides a map abstraction that you can have applications build on top of. Like Brian will sort of cover some of the details of the intent framework. You can see this in action at that point. So what we covered right now is essentially like one example of a state that we track in the control plane, right? But there could be other examples where you need sort of more stronger consistency, and here are some of those examples, right? So switch to control mapping is something that I touched upon. Resource allocations is another example where you are trying to keep track of the network resources and who has what at any given point in time, right? And in all these cases, I mean, it would be desirable to have a solution that offers strong consistency, primarily because it lets you sort of build better abstractions on top of a foundation which is strong. So the classic way to do sort of provide strong consistency is you can either do like a two-phase commit over a set of replicas, or you could do consensus-based protocol. But I think with two-phase commit is that you actually expect all the participants to be available. Otherwise, you cannot guarantee liveness. Consensus, on the other hand, only requires a majority to participate and then sort of commit. So given that availability is one of our goals here, consensus is an approach that we chose to provide state management that requires strong consistency. But a problem with sort of achieving consistency through consensus is that it actually doesn't scale well as you sort of increase the number of nodes in your cluster, right? So what happens is that you are essentially funneling more and more requests to the master, and when you do that, the sort of the throughput goes in the reverse direction of the size of the cluster. So how do you still build a solution that addresses this problem, but also provides the guarantees that we need? So here's sort of like a description of how one might do that. So this is sort of a graphical representation of the key space, and what you do is if you essentially partition the key space into smaller chunks, and you do sort of consensus over like each individual chunk. So whenever you have an update, you map that to the partition that it resides in, and then submit it to the sort of the replica group that is responsible for maintaining consistency of data that falls in that partition. So what's the cost of this approach, right? So as long as you have all your updates landing in a given partition, like the updates or like the operations are quote unquote cheap. You still need to go through consensus, but the idea is that you could sort of achieve it with one round of consensus. But if you have updates that span multiple partitions, an example could be if you're trying to sort of make bandwidth reservation over a series of links to satisfy a given intent, then you need to be able to atomically reserve the bandwidth across all those links. And it is possible that those links could be sort of managed or sort of stored in different partitions. So when that happens, the approach that we take is essentially run a two-phase commit across those shards. The problem I described with two-phase commit being unavailable is mitigated here by the fact that each replica group is not a single node but a cluster of machines that that are responsible for ensuring availability of that shard. Again, as I described earlier, so the way we sort of package this and then provide it to applications so that they can build on top of it is we have this consistent map abstraction, which provides a stronger, like think of it as a concurrent map in the Java context, but it is distributed and partitioned. So applications can use this to sort of like do their state management. So that gives us an opportunity to it provides a simple solution for applications to consume and then sort of build their logic.
It was KVT, right? It becomes KV here?
So the T in the eventually consistent map is the timestamp.
Okay.
So there you need to be able to, the way we sort of identify ordering is based on timestamp. Here, like the approach we take is like you get serialization through the protocol. So you don't need to provide like an external event timestamp. So that sort of like covers one of the sections that we wanted to deep dive on. I know that there are questions. We'll gladly take that during the QA part of the talk. So next I will hand off to Brian, who will cover the ONOS service APIs and also basically do a deep dive on the intent framework, for which there is a lot of interest. So with that, I will hand off to Brian.
Thanks, Madan. As he said, I'd like to first just talk about some of the APIs we have built into ONOS, talk about the intent framework, and then try to do a quick demo before the questions and answers. So just to show you this slide again, we logically break up the APIs available into ONOS into three major categories. The northbound APIs, which are typically application-facing, the core APIs, which are available as building blocks, and the southbound APIs, which are typically network or device-facing. And so, sort of seen another way, we can sort of talk about some of the different types of APIs that are available in the system. It's API-based, not necessarily based on other mechanisms other controllers use. But so starting at the core, this is the foundation of the controller cluster. The core service provides the ability to register some basic applications. The application service enables you to deploy an application to a single node and have it and its state replicated to other parts of the cluster. We have a cluster service that manages and maintains the cluster. From there you can figure out what nodes there are, who you are, and who's available. There's a communication service that makes unicast, multicast, and by multicast I mean point to select set of points, and broadcast easy. We have an event delivery service, which is useful for delivering events to other layers of the system. A storage service, a leadership service, mastership service. Basically, we have a set of primitives here in the core that will make it easier to write the southbound and northbound abstractions. On the southbound side, and again, this is sort of a logical distinction. There's nothing in the code that says you can't call whatever API you want. You have a device service which manages the devices in the system. And just to show you how these things start to build on each other, the device service will use the mastership service to figure out whether it is the master for a particular device. It'll use the communication service for sharing information. It'll use the cluster service as well through, well, the master service depends on the cluster service, etc. We have a link API, which is how you can get an inventory of the links available and the statistics and information about the links. Host service, which is for end station tracking. Stats service, flow rule service for programming the flow tables or for programming the tables on the devices. Packet service for receiving and sending packets in the network. Resource services, for things like label allocation and bandwidth. And then we have this notion of providers, which is sort of all lumped into the southbound. But basically, this is how you adapt to different types of protocols. And then on the northbound side, this is sort of how we start to synthesize some of the information that the southbounds do. So the topology service takes device, link, and host information and puts it together in a view that's consumable as a graph. We have a path service that's capable of computing paths in the system, and you can provide some basic constraints. And then finally, the intent service, which is the primary mechanism for putting requests into the controller from the applications. So all of these services are built using sort of a similar template. The idea is that you have a service API, which is going to expose sort of the building blocks or functionality of this service up to either other services or applications. We have an admin service API in certain contexts, which enables you to sort of administratively make policy decisions or administratively manipulate some of the data that this component is responsible for. In the case of the southbound protocols, we have what we call adapter services and registries. This is how you can register OpenFlow 1.0, OpenFlow 1.3, netconf, TL1, whatever you want, to the controller framework. And then sort of for managing east-west communication, there's an interface that a store will implement. The manager component is what we call the implementation that sort of ties all of this together. And then, like I said, on the northbound, you can have listeners for events that are going to be emitted by certain subsystems. You can actually make specific queries or make requests to the subsystem. And the store makes sure that whatever the consistency requirements and the data sharing requirements for the component are handled. So the subsystem looks like one system across the cluster rather than a per controller system. So I'll dive into the intent framework because I guess our time here is limited. But I guess at a high level, the intent framework is really two things. The first is it's a programming abstraction. The idea is we have intents, which are models for specific types of behavior. We have compilers, which is how these high-level requests get sort of converted into something that the data plane can make sense of. And then we have installers, which are responsible for taking those requests and turning them into the rules that is going to provision them on the data plane. So that's the sort of programming part. The other part to the intent framework is the actual execution framework. So an intent comes into the system, it needs to be stored, it needs to be compiled, it needs to be run through the compilation installation, it needs to be maintained when the network changes, and the framework piece is the subsystem part that's responsible for managing these intents. So to start on the programming side, an intent is a high-level interface that focuses on what should be done rather than how it should be specifically be programmed into the devices. What it does is it raises the level of abstraction above the devices, and it lets you start to think about what types of services you want to build on your network rather than how those services need to be implemented on the specific hardware that you have available. It helps abstract the complexity of the network away from the applications when they don't need it. One of the advantages of sort of the multi-tier approach, and also even within the intent framework, sort of lower level and higher level intents, is that when you do care about certain types of complexity, you care about the specifics of a particular path, or the selector that should be used, or the types of traffic you want to filter on, you can make those requests and the framework will take it into consideration. But the point is that you don't decide at the very beginning what exactly needs to be done from end to end. And then the other thing is that these intents should be easily extended, so that if you want to take building blocks and sort of build up higher levels of abstraction because it's useful for your application and you want to reuse them, the intents should facilitate that. So just to sort of make this concrete, I thought we could start with a simple example. A host-to-host intent is an intent that specifies bidirectional connectivity between two end stations or devices in the network. And so the first step is to model this. And one way you could do this is specify a class. Here it extends a connectivity intent, which is an abstract primitive that helps you build intent objects. And all we need is information about what the names of the hosts that we want to connect are. We can have constructors that make it easy to build simple versions of this, or we can have more complex constructors that make this a bit more extensible by allowing people to change the filter or the actions that need to be performed on traffic along the way. We can impose constraints like the bandwidth requirements, latency requirements, nodes that need to be avoided, or waypoints that need to be included. But the basic first step to the intents is to model them, and to model the service that you want at a high level. So the next step is to take that high level object, which knows nothing about the network, and figure out how it maps to the elements in your network. And this is a step we call compilation. And what we want to do is we want to take that high level request and map it into specific paths. So we still call them path intents. We're not talking in terms of devices yet, but we are talking in terms of devices from a path context, not necessarily how we install or get this service implemented on this thing. So the job of the compiler is to produce more specific intents than you previously had. In this case, we go from a single host-to-host intent to multiple path intents, given the environment. And you want to work on high-level network objects. So these are the objects available via the topology. The topology is a subset of the information that's available in the providers on the local devices and the local instances of the cluster. But at a high level, how can we map this high-level request into lower-level requests such that we're able to eventually get to a point where we've named specific devices that we can write specific rules for. We explicitly wanted to make these stateless, and by stateless what I mean here is that they're free from high availability and distribution concerns. If a node fails during compilation, what we want to be able to do is not have to build in that complex logic into this this unit of execution. These are going to be things that are built not necessarily just by us, but by people that want to implement services on the framework. And so from a compiler's perspective, if you fail, it's okay. We'll just restart that job somewhere else. And the interface is really, really simple. You just have one method.
Only for local, right?
Sorry?
Only for a local shard, or is it global? Right now, the path computation is
So this path computation is just for a single intent.
okay.
The part about sort of doing global traffic engineering is sort of a separate piece that we're not going to cover in the talk tonight. But for a given intent, how could that intent be mapped to the devices that you have available in the topology?
So intent to local, you are talking of an intent only to the local slice, shard.
So actually, you can go from an intent to the global to the global graph. So this process of compilation, because the topology is available on every node, will enable you to look at all nodes available in the topology, and then on a single instance make a decision about the resources that will be required. The actual reservation of those resources and installation comes next. So to make this a bit more concrete, how would you write one of these things? Well, we need to extend the compiler interface that I just mentioned. Here we'll call this host-to-host intent compiler. We'll get the two hosts from the host service. Remember that we just track the IDs and we want to get more information about them, like where they're connected, what their IP address is, what their MAC address is, so that we can make decisions about how the traffic needs to be forwarded. The next thing we can do is we can leverage the path service. Given the first point and the destination point and the constraints that may have been specified in the more complex constructor, return to me some paths that would satisfy this request. We'll get the paths back, and here we have some magic algorithm. It's pretty trivial in our basic implementation, but if you're writing one of these compilers, you could have some heuristics for picking paths, depending upon available bandwidth or GPS hops or whatever you want. And then in this case, we want the path to be symmetric. So we just invert the path. We'll get the reverse path, so we're going to program a path that follows the same links in both directions. There's an assumption here that all links are bidirectional. That's not necessarily true, but for this simple example, I think it'll suffice. Finally, what we want to do is we want to generate those path intents that I mentioned. We give the path, the endpoints, and the parent intent to this method that's going to call a constructor on the path intent, and we'll do that for the reverse path as well. And then return these two path intents as a list to the framework. So this is all that would get executed. This is all the code you need to write to sort of implement a mapping from a high-level intent to a lower-level intent. And this can be recursive, as many steps as you want. So this could generate some intermediate-level intent that then is going to get sort of further compiled by some other piece. So after compilation, we actually finally get to a point where we've named all the devices, we know what links are going to be used, we know what path is going to be taken, and we need to actually provision this thing onto the data plane. And we call this process installation. It actually comes in two parts. So installation is the process of mapping the path that we said into the flow rules that describe the policy that needs to be pushed down to each of the nodes along the path. So in this case, this path intent is going to map into two sets, the tail and the head, and this one's going to map into another two sets, the tail and the head. And so this process we call installation. And the idea of these installers is to transform the intents into device-specific commands, still at kind of a high level using object abstraction. Allocate and deallocate network resources. So if this intent required a bandwidth reservation, if it required an MPLS label, a VLAN label, a Lambda, whatever, that allocation needs to happen here. Define the scheduling dependencies for the workers. So the scheduling dependencies is do this first and then do this. If you care about the order in which things are done, that information is passed off by the installer. And again, these are stateless in the same way that I meant by the previous one. Not that they don't have access to other components, but that you don't have to worry about HA and distribution. If you happen to make a reservation in this step that that needs to get backed out, the framework knows how to do that. When you try to run this again, it'll look to see if you have any existing reservations, and it'll let you know about them and let you amend them if you want. But the idea here is that The installer is simple. You write it thinking that it's going to run through to completion, and if it fails, then the framework takes care of rerunning it somewhere else. And so again, to make this a bit more concrete, we can show you some code. I didn't implement the whole thing on this slide, but again, we have a path intent installer. It extends the intent installer interface that I just showed you. And basically it needs to do three things. Install, so basically provide an initial set of flow rules if you've never seen a policy like this before. A remove, so how do we get this off the data plane? And then a replace. So given an old version of your policy and you want to move to a new version of the policy, you may have some resources that are already available, you may have some policy that's already been provisioned on some of your devices, and the replace basically lets you reuse pieces of work that have already been done. But we'll just focus on install for now, because that I think will illustrate the point well enough. The idea here is, first we allocate some resources that were requested by the intent. This would be specified by the path intent object. We'll get back that list of allocations. In this case, we don't actually use the allocations in the simple example, but in the real code you'd actually want to use the label or the queue or whatever it is you got back from the allocation. And then the next step is to build the rules. So, like I said, we want to construct a rule for every hop, for every device. And so we can iterate through the set of links that we have. So we can ask the intent for its path, get all the links that are available, and then we can create a flow rule given the link that we're taking, the link that we're currently considering, and the overall intent to produce a rule for the device that will ensure that the traffic gets through the device to complete that part of the path. We wrap this rule up in an operation, which basically just includes add, remove, modify. That's the basics. And then we return a list of these things. The list basically enables you to specify ordering. In this case, we'll just do everything at once. In reality, if you want to make sure that some operations are done before removing other operations, for example, for smooth switchover, you may provide as many sort of stages as you want. So I guess the final step here that we actually don't do in the intent framework, but is done by another subsystem, is the actual provisioning of these policies on the devices. And so, for example, if you have a network that spans, or a path that spans 6 switches, and 2 of them are controlled by this node, 2 are controlled by your neighbor, and 2 are controlled by another neighbor, we give the group with the dependencies, basically this list of collections of flow rule operations, to the flow rule subsystem. And the flow rule subsystem manages the problem of getting the actual flow rules to the appropriate point in the network that's going to do the installation, and then collecting the barriers back, and then only proceeding on the next phase of work once all the barriers have been received. It sort of looks like a 2-phase commit procedure. But when that's all done, then the flow rule service will call back and say, I've installed this batch of work, we can annotate our state, and then mark the intent as installed, so that if you were an application that cared about this, you could see what the state of the request that you've made is. So that first part was sort of the programming model. In order to do programming, you need the models, the actual intent objects themselves, you need the compilers, you need the installers, which are going to describe how the work gets translated down into device instructions. The framework, which I mentioned, is the part that actually sort of does the magic. We have the intent service API, which is how applications communicate with this service. It enables you to register the listener, as we talked about, submit intents, withdraw intents, submit new intents, overriding existing intents. And that service API is implemented by the intent manager, which is sort of that same glue component that I showed in the initial template diagram. There's another API that the intent manager implements, that's the extension service API. And so every one of the intent compilers and installers gets registered through this extension service API. And that's how the framework knows how to find the compilers that are required for the intents that are registered with the system. And the idea here is that you can modify the behavior of the intent object by writing a new compiler or an installer. You can write your own intents that have new semantics, or you can sort of mix and match. You could modify objects and then tell them to use the same old compilers. Basically, the extension service manages a mapping between the intent object class and the code that's going to be executed when required. The intent manager and the intent store work hand in hand. The manager sort of does the glue work and does the grunt work of kicking off the installers and the compilers when required. But the store is what effectively manages all of the intent objects. And so the intent store, I'll talk about it more later, but that's the one that actually distributes the intents to make sure that if there is a failure in the system, that we can recover. The intent manager also, yeah, sure, question.
On this path intent, right? You showed this get path when you try to install a path.
Yep.
How does it know to identify that? How is that path identified? Path calculated?
So here, this one here.
Get paths, yeah.
Get paths.
Yeah, who's doing the work underneath to get the path?
So what we're using here is what we call a path service. And so the path service is another one of these service APIs that lets you specify 2 points and some constraints. And then we basically use a modified extra that will only pick paths that meet certain constraints. But you could implement your own logic here. And this, as long as you implement the service API, you could have specialized algorithms for doing path computation. But the default out of the box one is a modified Dijkstra that basically, actually, sorry, it's not a modified Dijkstra, it's modified k-shortest paths that knows how to handle constraints.
But this can also be a layer 2 path, right?
Sorry?
This can also be a layer 2 network.
So we don't actually care what layers you're talking about here at all. We just know that you have certain devices that are connected in certain ways. And the assumption is that the end devices need to be able to filter the traffic and sort of forward the traffic that you're going to talk about. But if that has to, if sort of the layers need to change, if you need to go from an L2 to an L3 network, or from L3, say an MPLS, L3 MPLS core to an optical core, that doesn't matter. The path here that would be described would sort of contain all of the hops, and then it would be the job of the installer to interpret the changes in technology.
So after you install a path, let's say a link goes down.
Mm-hmm. Yeah, so that's the next part. I actually won't talk about it a lot, but the intent, the other 2 parts that are used by the intent framework are workers. So these workers are actually the pool of threads that are used to do compilation installation. And then the objective tracker is a piece of code that monitors the network. It listens to topology events, host events, link events, flow events, and when there is a change in either the network or the network state, it identifies the intents that are affected because it keeps basically, you can think of it as like a cache secondary index. It keeps a mapping from resources to the intent keys. And then whenever it detects an event that could have affected one of the paths, it tells the intent manager, hey, you may want to recompile this intent. So
typically, how long does it take for a reasonable size network, for a link goes down? How long does it take for the traffic to recover on an alternate link?
So what you probably want to do in a real network is actually program a backup path into the intent. So you want to say that the intent has a primary path and a backup path, or even an ECMP path that equal cost multipath path. But in the case of just reacting, I mean, the reason you want to react is because when you do have a link fail, you've effectively changed your traffic matrix, and you may not have another backup. And so you want to recover as quickly as possible to maintain an alternate backup, and also so that you can sort of readjust any differences in traffic load. But the times that we see are in tens of milliseconds to react to the event, recompute, and then reinstall. It sort of depends upon how much latency is between your devices and your control plane. That's the bottleneck. The recomputation is actually a very small percentage unless your latencies are close to 0. Yeah, question?
Different question. You know, before in the previous presentation, we talked about multiple controllers, right?
Mm-hmm.
Does the intent managers run on multiple of them, or how does the map to those? How do those things link together? Or does it
Right. Okay. So the question is, we showed a distributed cluster of instances in the previous part, and now it seems like we have this intent manager and it's only running on a single instance. And so the answer is that we actually use a symmetric deployment design in ONOS. All of the major components are running on every instance, and the idea there is that if any instance fails, then any other instance can take over the work, and that work can be redistributed. So the store is actually the only component that is really cluster aware in the whole framework. And I'll get to that in just another 2 slides, but you can think of every one of these components running on every instance of the cluster. So to get a bit more concrete in the framework, there's basically this intent abstract class, the base intent class, specifies an important feature. I just wanted to call out the key. So a key is a user-specified name, shall we say, for this policy. If you don't want to name your policies, we can name them for you. There's an internal ID that we can just use to derive a key if you want. But an intent basically tracks the application in which it originated, and then a key, which is a name for a policy, which is what applications can use to withdraw their request, or if they want to change their request later, they use the key. And then also intents specify a collection of network resources that are required for the operation. The other thing, the service interface that I just talked about on the previous slide, this big bar up here, the primary mechanism for applications to use, specifies a submit, a withdraw, and then a get intent. There's a bunch of other methods for listener registration, for understanding what the state of intent is, and some other things, but that I think would be better to look at the code. But the important pieces here is submit and withdraw. The intent manager then is responsible for implementing those simple methods. And to do so, I just wanted to show you, it leverages other components in the system. So it depends on the core service. That's how it generates the blocks of unique internal intent IDs. It leverages the intent store, which I just mentioned, the objective tracker. It leverages the event delivery service. This is how it delivers. It manages the listeners for its types of events, and it dispatches the events using the dispatcher. And it also leverages the flow rule service for installing the rules and reporting success or failure of whether the intents have been installed or not. And then, like I said, there's the implementation of those methods that's available in the source code if you're interested in specifically how this is done. The next part, the cluster-aware part of the intent framework, and this was done specifically intentionally. The idea is sort of confine and contain the distributed part to an interface, so that you don't have to worry about what happens in failure scenarios, what happens, across the cluster. From the intent manager's perspective, it's just its view of the world. It does the work that the store assigns to it, and then it reports the success or failure of that work. And so really the store is the key to HA and scale out for this framework. Work is delegated to a specific cluster node through logical partitions based on key. So an intent is submitted from an application, and with that key, that application key combo sort of uniquely identify the policy, and then that maps to a logical partition. So we basically take a hash of that key and app ID, and then we figure out which instance is going to be responsible for doing this work. Like I said, the execution steps are designed to be idempotent. We have some handling for when resources are required, but failures are detected by the store. If it notices a piece of the cluster goes down, it will automatically identify a new master for the logical partition, and then reassign the work and redelegate the work to the appropriate intent manager. So I think I have, after this slide, one slide that sort of walks through that a bit better. But from the store's perspective, we have a store interface that's basically read, write, add new request, and delegate to the intent manager. And the intent service is where we see the dependencies on the cluster service. So that provides information about what other nodes are available in the cluster. The cluster communication service, which is the mechanism we use for map updates across the cluster. And then we have a partition service, which is how we define the logical partitions for the intent framework, and also elect and maintain the leader for each of those partitions. You can note that we use the eventually consistent map, similar to the topology, for pending, which is the requests that have not yet been processed, and the current state map, which is the intents that are currently actually pushed down on the data plane. one thing to note here is that we use the eventually consistent map here in sort of a slightly different way than we do for topology. But every instance does have access to all of the high-level policies. So if you wanted to do some conflict detection, or you wanted to do aggregation of policies, every instance does have access to the high-level requests. That's not true necessarily for the flow rules that are generated. So the artifacts that are generated actually are going to be sharded based on the devices that they affect and the instances that are responsible for controlling them. But for the high-level policies and the topology, these are globally available. And then for the artifacts that are generated, they're sharded. Obviously, resources that are required, those reservations are also sharded. But this is sort of how you build or start to build the store and how the dependencies figure in. So this is sort of the high-level picture that maybe explains the interaction a bit better. An intent, this little orange box up at the top, is submitted to the manager through the intent service API. That box is wrapped up in what we call a metadata object, which contains a timestamp that the request was made. Again, this is a logical timestamp. And then that timestamp data, we also write some information about who made the request and stuff. That's passed along to the store. The store reads the key, decides which partition this intent maps to, and then will unicast the intent to the appropriate master. It'll also pick up backups and send the intent there as well. Then on the master node, if the intent is the one, if this instance is the one that's been delegated to do the work, we will give the intent back to the intent manager. This is where the framework step happens. The compilation happens, installation happens. We write down to the flow rule service, and then when the flow rule service gives us the OK, we go back to the store and write the update. So you can sort of imagine this being the pending state. So intents that come in, they sit in a pending map up here while they're being while the work is being done. That also helps us identify if there's a failure, if something's sitting in pending for too long, then that's one indication. Also a change in the logical partition also is another indication. And then once that intent has actually been processed, it sits in the current state map in the bottom. And so the flow is sort of from the app to the manager. The store handles the HA distribution part, and then for the work that is going to be done locally, for the work that you're the master for, you'll do it and write back to the store. These arrows over here just indicate that you're going to communicate the updates to both of these maps to at least a few other instances in real time, and then the anti-entropy mechanism will handle synchronizing these maps and so on.
Question.
Sure.
So how do you handle the situation where the data plane and the control plane are out of sync? There could be any number of reasons where the data plane entries might have got corrupted, and you don't have an event going back northbound.
Right. So the question is, how do you handle cases where the data plane and control plane become out of sync? And so there's actually a lot of lower level subsystems in the intent framework that drive the data plane and the control plane to be in sync. For example, if for events that originate on the devices themselves, those events we hope to see at least once. When there's changeover in Mastership, we also will pull the switch for the state of its devices, or the devices for their state of their ports of themselves, whatever. So the device service, the link service, will actually drive to be as consistent as possible with the actual physical data plane. Now for the policies, the flow rules or whatever you want to call them, that are going to be written down to those devices, we actually leverage I guess, if we can't get those rules done in the first iteration, we'll leverage the stats polling to detect when there's an inconsistency and then reassert the rule back on the switch. So from the device's perspective, the state that they're sort of the truth for, that's sort of driven up through the system, and the system works as quickly as possible to get consistent with that state. And for state that sort of resides, the truth resides in the controller, the lower levels of the lower levels than the intent framework, the flow rule subsystem and below, work on driving that state down to the devices and maintaining that state on the devices. When those subsystems are incapable of doing so, then they kick up the error to a higher level framework like the intent framework, which then has to take action, maybe avoiding this device in the next round. Yep. Question in the back?
So what is your typical use case, like across data center, inter-data center, and how do you deal with high availability, high stability?
So what's a typical use case for the intent framework, or what's
for your entire networking OS?
Oh, so the recommended deployment model for ONOS so far is to run a cluster within a data center. So you run a cluster within a data center, you have low latency, high bandwidth communication between instances. You could, if you wanted to, run across data centers, but there'd be a pretty significant penalty for sideways east-west communication between the instances. And if you're willing to pay the penalty, it's mostly performance, not correctness.
So right now it's a hierarchical or flat?
So the clusters that we're talking about are flat, but I think as Madan alluded to, the idea is that you're not going to run a single cluster for the world's network. We don't have a good hierarchical story just yet, but there are some models that we're looking into. But the idea is that you have a single, I guess you could call it administrative domain or subset of your network that makes sense to control as a unit. And in that unit, you're going to have a cluster of controllers that are going to have a full view and that are going to manage that part.
So it's not a commercial project. It looks like a school project, right?
Sorry?
A school project?
No, this is a commercial project. We've got a number of really serious partners, including AT&T, Huawei, Fujitsu, and TT, that care a lot about this and are deploying it. So we're not talking about a lot of the use cases here, and I think this may come off as sort of simplistic in cases, and that was mostly done to help facilitate the communication of ideas. But we do have a lot of really serious use cases that are built around this. A lot of the implementations that you'll see in the actual repositories are much more complicated. And it just, for the purpose of sharing the ideas, we thought it would be easier to try to simplify, break them down. So there's a question in the back?
Yeah, how much data is in the store? How much data are you talking about here? And how quickly is it changing?
So,
is there any rule of thumb, kilobytes per device sort of thing you come across?
There are, I have a table, and unfortunately it's not on this deck and I don't have easy access to it. But, so the question was, what are the sizes of data we're talking about? And I think rather than think about the size of the state across the entire cluster, we like to think about the size of the state per subsystem. And so for something like topology, you've got maybe at most thousands, in the order of thousands of switches with not much, maybe a few kilobytes of data per switch. So we're talking about sort of on the order of megabytes of topology information. When we talk about intents, we're talking about maybe on the order of hundreds of thousands, maybe up to 1 million sort of intent policies, high-level objects, which each are, 100 bytes. When we talk about the actual provisioning of flows onto the data plane, that's when the data starts to get a bit bigger. We could easily turn a single intent into 6 or 7 flow rules. That's that's sort of assuming a 6 or 7 diameter on your typical path, and that's where it gets bigger, and that's where we start to shard data. For things like stats, very quickly gets very large, and so what we want to try to do is maintain some live and some short duration history, and then you want to write that to some streaming database outside of the controller. I guess it's sort of hard to quantify the exact amount, but I think we're talking about something on the order of at most tens of gigabytes of sort of active state per node, where some of that state is going to be sharded and some of it's going to be fully replicated. Sure.
So you have a host intent for every pair of hosts that's communicating. That is statically set up for every single VM that's talking to some other VM. Is that a correct understanding?
So that's one way you could do it. So the question is, you have a pair of host intents for every single pair of hosts you want communicating. And so one way you could think about implementing this is you could have a host intent that describes every pairwise communication pattern. That's probably not the right pattern if you're going to have, say, groups of hosts that you want to talk to each other. You may want to set up a sort of a group that enables communication within a group. That could be based on something like an IP address. And on that, you want a different intent, not a host-to-host intent.
No, where I was heading was, let's say that VM migration happens, let's say vMotion happens. How do you recompute the intent at that time? Is it dynamic? Is it driven done automatically, or there is a user intervention required at that point to recompute the intent?
Right. Okay. So the question is, if there is something like a VM migration that happens, a host moves from one point to another, how do we deal with that? And that's actually one of the biggest advantages of actually naming high-level objects, like high-level abstractions like a host, rather than talking about an IP address or a MAC address. Because if you are listening to host events, what you'll notice is that you get a notification that a host has moved from one part of a network to another part of a network. And when that occurs, the intent framework will know that for this host, I'm tracking these intents are the ones that use or rely on that host. And for those intents, those need to be recomputed. When they get recomputed, it'll realize the location's changed and it'll perform the rerouting.
How do you get that notification? Who sends the notification? Host migration?
So the host migration notification will be handled by the host service.
No, like who's sending it? Let's say you have a Linux-based installation.
Okay. So who's sending it?
Yeah.
So one way you could do it, if you didn't have help from an orchestration tool like OpenStack or something, is you could detect the migration by, say, like an ARP or something on another port. So if you detected the movement, you could do it reactively with a reactive host provider. If you had something like a OpenStack or other VM management tool, it could tell the controller that this host is going to move from this point to this point, and then the provider, the southbound layer that interfaces with that component, would register that event with the topology, and that would be propagated up to the intent framework. So, yeah, question in the back.
Are your use cases available on the website instead?
They are. And so there was actually a hidden link, not hidden, it was in the bottom of one of Madan's slides. I'll provide a pointer to that, and maybe when we get into the live demo, I can actually show them to you. There's a set of 4 initial use cases that we're focused on. There's a number of other use cases that we're working on. One of them is, just to sort of enumerate them quickly, one of them is SDN IP, which is basically a BGP router implementation on a pure SDN network. Another is a segment routing application that uses global MPLS labels to do routing, both default routing and select path routing. We have a central office use case for NFV, so doing routing through virtual network functions in the data center and coordinating load balancing and migration of those functions across servers. And there's another one that's slipping my mind right now. IP RAN is one that Huawei is driving, that they've also done some demos for as well. Sorry? IP RAN? Do you want to talk about it, or maybe?
It's for a radio access network.
Yeah. Okay, so maybe we can just drive through. I think this is actually one of the last slides. But one of the things I wanted to highlight here is that this intent framework, as well as the rest of the system, is designed for modularity. And this is just one example. So intents, compilers, and their installers can be defined and loaded dynamically via the extension service APIs that we showed. The framework implements a service API. So if you wanted to, you could swap out the entire intent framework and pull in your own implementation. And each of the components, the store, the objective tracker, and the workers, implement internal APIs. So they can be replaced as required. So if you want to change the behavior of the system, whether it's the path computation, whether it's the way in which flows are installed, the devices onto which those flows are installed, all you have to do is implement a small component that implements an interface that's expected, and the rest of the system can leverage that. So I guess the question, this is sort of getting at some of the points that were asked, what's next? So one of the things I'd encourage you to do is to join our mailing lists. We have a number: discuss, announce, developer. So if you want to ask us questions, that gives you access to the whole community. We have a number of tutorials that we put together. Some of them are basic, how you get the GUI up and running and how you use the CLI. Some of them are how you can start to build applications, simple applications, distributed applications that I encourage you to try out. You can get your hands on the source code via Gerrit, which is the authoritative repo, or via GitHub, which is a read-only mirror. We have the API Java doc available online. You can get the current master as well as all the official releases. File or fix a bug. If you find something you don't like, we have an open bug tracker that you can use. And then there's 2 links down at the bottom for the project page and the wiki. The wiki is actually where you can get access to the use cases. I can show you that in just a second. So with that, this is sort of the time for the live demo. Maybe we'll abbreviate it slightly. I think originally we were planning on trying to show a pretty extensive code walkthrough, but maybe this isn't. Maybe it'd be better to let you do that on your own and maybe just provide some pointers. But I can show you the. Sorry, 1 second. Unfortunately, the guest network here doesn't let me use VPN. But So while that's reconnecting, one of the things I wanted to show you just briefly, so you kind of know where to start, and unfortunately this is kind of small, but the code is organized into sort of a number of major sections. There's an application section here, which contains application code. A lot of the use case specific code is in here. There's a proxy ARP application for doing reactive host tracking, and also proxying ARPs around the core of the network. There's a routing application, SDN IP application. There's a bandwidth calendaring application, a BGP router application. So here's sort of a good place to start. These are smaller components that leverage the APIs in different ways. There's another big bundle which I wanted to point out, which is the core bundle. And this is where the major subsystems that we talked about are. A good place to start here might be the API package. And so here you can see that there's a number of APIs. The cluster API, Mastership API, net is where most of the device intent topology stuff is. Store APIs, and then the implementations of those APIs are in these parts of the package. So that's sort of a quick overflight. Apps are a good place to start, then core is another good place. There's a lot of supporting code for CLI, UI, and some of the other southbound protocols that's elsewhere. So here's a quick view of the UI that comes with ONOS. Cheat sheet here. In order to see what commands you have available, you can hit the question mark. But I can show you quickly sort of some of the major features. So at the top of the screen, you can see the instances in the cluster. Here I have a 3-node cluster set up. The IP address is shown. You can name them if you want. Also, we've got the switches that are attached, the number of switches attached to each one. It's hard to see here the difference between orange and brown, but the mastership for these switches, the devices in the network, is shown color-coded on the topology. This happens to be a slightly modified version of a nationwide MPLS backbone. But the point here is that you can overlay a map if you want in the back. This could be sort of a site map for your data center. It could be for your region. Here it's the US. That can be turned on and off using a keyword shortcut. Over in the top right, we have a summary of the cluster. There are 25 devices connected. It's been configured with 112 links. We've got a host hanging off of each of these links. Those are the small little boxes that are usually hidden. And then one strongly connected component. So we basically have a single network. There's no separate parts. There's 60 flows in the network. These are default flows that are provisioned automatically, and no intents yet. A couple other things we can do. We can turn off the summary view. We can turn off the instances view. We can get details for any one of these devices. And so this is a switch in Chicago. Here's its unique identifier. Sorry if this is a bit small. It tells you that this is an OpenFlow switch, talking protocol OpenFlow 1.3. Its master is what you said, and then we've annotated it with longitude and latitude. So these annotations, like longitude and latitude and other things that you may want to introduce, can be added to the models that we have. This is a switch with 11 ports and, like I said, 5 current flows. One of the cool things which really helps for debugging, I think, and it's sort of hard to see, but as you hover over some of these links, you can see that it'll show you the port numbers on either side of a link, so you can tell whether the links have been done. And we support 2 modes of operation when it comes to registering devices and links. Either you can proactively tell us about them via a REST API or using the Java APIs directly, or we can try to discover them, and you can enable or disable that if you want. So these are all, these devices are all proactively positioned, but if you wanted to just attach a random topology and have the controller discover the links, it can do so using LDP. Another thing that you can do here is you can ask the controller to provision an intent. And so I'll select 2 nodes and then ask it to create a host-to-host flow for the demo. We can see the path that was selected. Here it's highlighted in orange. And we can sort of do this across the network. Like I said earlier, if you wanted to do this for every pairwise host, you may want to reconsider the abstraction you're using, but you can do it. So this will show us on this device the related paths. We can pick the path that we want. If we run some traffic over this network, we'll see that communication can happen between those nodes. So this is, let me try this. All right, cool. So here's sort of a quick view of the network. It's the 25 switches. We're running MiniNet here. We don't have this connected to a physical topology, although we could have. And then what we can do is, and host 15 and 14 are represented by this orange path. I can ask host 14 to ping host 15. And the first thing you'll notice is that connectivity works here. If we picked a random set of hosts in the network, sorry. Oh, sorry. Cool. So if we start the traffic flow between 14 and 15, we'll see that if we turn on traffic, we can start to see some byte counters increase. These will periodically be pulled from the switches. And there's no traffic on this, there's only traffic on the one path that we've selected. So the other thing that I can show you quickly is that we've got a pretty full-blown CLI. One of the things you can ask it for is intents. It'll show you that we've installed 2 intents here. You can ask it for the devices, and it'll show you those. Masters, it'll show you which is which. You can also ask it for the features that it has currently installed. So this is based. So if you're familiar with graph, you can see, and this is really hard to parse, but what it'll show you is you've got a number of ONOS apps that are currently running, one of which is reactive forwarding, which will give us basically free connectivity. We're running OpenFlow, like I said, the CLI and GUI. We're running the core, the main core, the distributed core. We also have a trivial package if you want to just do some local development. That's in-memory implementations of the maps that we've shown. And then a number of other OSGI, either graph or physics packages. If we were to remove the reactive forwarding feature, actually, it's installed with an app. So app uninstall app forward. That ping that I didn't expect to work before will fail. The reason it worked before is because we had a feature turned on that basically just provisions reactive paths whenever they're requested on demand. But the connectivity for our provision flow, our host-to-host intent, still works as expected. So I guess what I can show you next is the API docs. So the Java docs that you'd expect are automatically generated from the source code, and you can explore the packages that are of interest to you. And at a high level, I think it's easier to start to understand the APIs via Java doc. Obviously, the source code's available if you want to dive in. We've got some basic tutorials. If you want to run the demo I just showed on your local machine, you can download a VM and get it started with a tutorial available on the wiki. Those are available in ONOS for newcomers, tutorials, and walkthroughs. We've also got sort of an increasingly difficult sequence of these tutorials, including a distributed ONOS tutorial, where you actually build a new service, one that creates virtual networks. It's a fully distributed application. It follows the same template pattern that we described in our earlier talk. And it probably would take a couple of hours, maybe a half a day to walk through. But at the end, you'd have a distributed store, you'd have event listeners, you'd have CLI commands. You could extend the GUI and put the virtual networks on if you want. So we're happy to sort of accept new tutorials if you have ideas, but we've got the VMs available on the website if you want to get started. Actually, the source code for the build your own network tutorial is also on GitHub. So if you care about cheating, it's all there. Well, using a reference, shall we say? But yeah, you can compare your solution to the one that we have. And, so that's probably a good place to get started. Someone asked earlier about the use cases, and so we've got a major section on the left side of the wiki here called ONOS use cases, and you can find out a lot of information about any of the use cases. Sorry, one of the use cases I was writing earlier, in addition to EPRAN, was packet optical. So that's basically a converged packet and optical network. You control both ROADMs and packet switches and routers. But you can click on any one of these, and there's sort of there's video overviews, and then there's descriptions of the product, guides for the tools that we've built so far, and the architecture for the applications. So with that, I think we're sort of getting near the end here. Yeah?
Yeah.
Okay. With that, I guess we can go back to questions and answers. Put on back up here. Sure.